Hello everyone, I'm Satyam Kumar, a third-year student under supervision of Professor José Millán at UT Austin. Today, I will be presenting our work on transfer learning framework for longitudinal motor imagery training. BCIs are system enabling communication between brain and an external device without the help of peripheral nervous system. It has range of application from rehabilitation to prosthetics to assistive devices and interactive devices. Motor imagery is a common modality to control BCI, where subjects mentally rehearse a motor limb movement without moving the limbs, but instead just imagining the movement trajectory. MI skill is a challenging skill to acquire, and unsurprisingly, it has been shown that user learning is crucial for modulating the neural correlates of MI. A machine learning model is at the heart of operating BCIs in real time. However, as user is learning a skill and our neural signals are continuously evolving over time, the machine learning model built on previously seen data perform poorly on the non-stationary data. The problem of non-stationarity is further exacerbated by trying to build subject-independent BCIs. However, there is one invariance that our brain has is similar spatial lateralization of motor cortex across subject. We pose the question, can we train naive BCI subjects exploiting this spatial invariance using a data of a well-trained MI subject to perform MI in real time? The Riemannian geometry-based approaches which exploit the spatial invariances by extracting covariance matrices between different channels as a feature has been promising for offline analysis in BCI. We prefer to use MDM due to its simplicity and robustness for classifying motor imagery tasks. MDM is minimum distance to Riemannian mean classifier on Riemannian manifold motivated from clustering-based algorithm family. MDM is parameterized by class prototypes, which are Riemannian means of covariances of different class. Conventionally, we have seen a lot of non-stationarities which result in drifting of the covariance matrices on Riemannian manifold due to cross-subject and cross-session variabilities, thus having a different test and train distribution. This is the classic case of domain adaptation problem in machine learning, where training and test data is different and decision boundary might fail poorly. To tackle this, we propose to use online incremental unsupervised Riemannian adaptation, which matches the incoming online data, which is naive subject data, to the transfer subject data up to first order, and hence providing a concurrent feedback for subject operating the BCI. We propose two real-time transfer learning frameworks, supervised and unsupervised. In an unsupervised framework, we just match the naive and transfer subject distribution. And in supervised framework, we, along with distribution matching, incrementally updated the parameter C1 and C2. All in all, we have crucial recentering step in our pipeline. We validated this on 18 subjects, 9 unsupervised and 9 supervised framework. We trained the subject to operate BCI through two different scenarios, a one-dimensional bar control and a discrete control based to deliver command to play a racing game. We did a calibration session to benchmark the performance, followed by 5 different online days where we asked the subject to operate the BCI in real time. Depending on the session, we either did 3 or 4 bar feedback or 4 or 5 race gaming runs. We compared the Kappa value of 3 different kinds of decoder. Briefly, Kappa is an analogous metric to accuracy, but is preferred to be used when the class labels are imbalanced. We use transfer subject as the decoder used in real time. Same subject recenters decoder simulated pseudo online in corresponding adaptation scheme. And this was to emulate how would have been the performance had subject-specific data is used. And same subject is decoder used without tackling any non-stationarities. We use pair t-tests to estimate the significance. We clearly see that for both the framework, the adaptive decoder was significantly better than the fixed decoder without any adaptation, which clearly highlights the presence of non-stationarity in the data. Convincingly, it shows that same subject recenter and transfer subject has similar performance. Next, we saw the online performance of the command delivery for both the modalities in bar feedback and raised feedback scenarios. We use linear mix effect model with fixed effects of time, which is session 1 to 5, and random effect of subjects. We clearly see that the performance significantly improved from online session 1 to online session 5 for both the frameworks, supervised and unsupervised, in both the scenarios. Finally, the key takeaways are: skip the calibration session, start the training with generic decoder. Online incremental adaptation helps. This was evident from the comparison performed pseudo online, where adaptive decoder were significantly better than the fixed decoders. We saw that longitudinal training helped subject gaining BCI control as performance significantly improved. And this was also observed in a more realistic scenario where we observed that race completion timing decreased and command delivery accuracy during the race increased.